Now let me summarize all we've seen on performance. So first of all, we've seen that execution time and memory use are very important properties. They connect the abstract execution of the machine to the real world, so they determine whether a program is practical or not. And in order to reason about that, we've introduced an approach called computational complexity. So we analyze performance using a technique called asymptotic analysis. So this studies what happens when the input size of a program increases without bounds toward infinity. And in order to do that, we've defined new mathematical concepts. So first of all, the big O notation, which defines an upper bound, the big omega notation, which defines a lower bound, and the big theta, which defines both upper and lower, which is also called an asymptotic equivalence. So in addition, it's possible that for a particular input size, there may be many different inputs with different complexities. So we have to look at the distribution, the probability distribution of the inputs. Are the inputs, do they tend to be easy ones for the algorithm or hard ones or what? So we have seen how to look at this with the best, average, and worst case performance. And finally, we've looked at practical issues. These practical issues depend on three aspects. So first of all, there's the hardware performance, which depends on an empirical observation called Moore's law on the technological development of computer processors. It seems that since the early 60s, as observed by Gordon Moore in 65, the transistor density is doubling every 2 years, and this is still going on now, so for almost 50 years, and it's still going to go on for a number of years. So a second point is program optimization. If your program is too slow, you can replace an algorithm by a more clever but possibly more complex algorithm. This is a very seductive thing to do, but in fact it's very dangerous and it should be resisted as much as possible. Finally, the study of algorithms has led to some fundamental understanding that certain kinds of problems, while they can be solved on a computer, can only be solved, it seems, with very inefficient algorithms, that there cannot, even in principle, exist efficient algorithms for these problems. And in fact, this is what we suspect. This is not even known for sure. So it seems that the class P is different from NP, and it seems that finding the solution to a problem is going to be more expensive than verifying a solution. But it's not for sure. Maybe it's the same. We still don't really know. So it may be the case that P different from NP will have to be considered a new physical law, like the laws of thermodynamics.